Hello, welcome back. So in our last video, we saw how breaking down an image into smaller blocks, such as 8 by 8 pixel blocks, it was possible to describe the image using a discrete Fourier transform for each individual block. We then saw how the original image could be reconstructed by adding up each individual DFT basis function to each individual block using the complex amplitude given by the DFT. And we saw two examples of this, one with a text-based image and one with an image of some ducks, so a digital photograph. We saw that we could get excellent reproduction of the original image for a digital photograph using relatively few of these DFT basis functions, and similarly, for the text-based image, we saw how breaking it down into blocks actually improved our ability to reconstruct it when compared to computing the full discrete Fourier transform. And so there appears to be an advantage to breaking down an image into smaller blocks and then performing the discrete Fourier transform on those individual blocks. In this video, we're going to be doing a comparison between removing components from the full DFT for an image versus removing components from the individual blocked DFT. And what we will see is that for a digital photograph, removing information from the DFT and from the block-based DFT produces similar images up to around a reduction level of around 99%. Beyond this, blocking artifacts become present in the reconstructed image when using a block-based transform, whereas in reducing the DFT components results in a sort of grain or blur. Perhaps this is better seen in the text-based image, in which the original image, when removing the DFT components from both the full discrete Fourier transform and for the block-based Fourier transform, we see very different results between the two. We can see that removing components from the DFT gives artifacts over the entire image, whereas removing components from the block-based DFT produces artifacts that are localized around the text. So we'll be producing these two comparison videos. Let's get started. And so the way we're going to structure this video is first we're going to create a plot, and the plot will contain space for 3 different images, with the images on the left being the original image, a copy of it, the 2 plots in the middle column being the discrete Fourier transform and the block-based discrete Fourier transform, and the images on the right being the reconstructed image from both the DFT and the block-based DFT. In both cases, we're going to go ahead and start to remove information from the original DFT and from the block-based DFT, and then see what happens as we reconstruct the image. Let's get started. If we recall from the second video, you'll remember that we produced the following image, where we had 2 copies of the original image on the left, 2 discrete Fourier transforms on the right. So we can go ahead and copy most of this code over. So all our imports at the top, these are by useful functions. Block size is a variable we still need, because when we're breaking down our DFT into blocks, we want to go ahead and load an image. We need to ensure that the image is an integer number of block sizes across. So if the image is slightly bigger than, if the image is not divisible by 8, we crop the image until it is divisible by 8. We then take the aspect ratio of the image, because remember, we're going to make it so plot takes into account the aspect ratio of the image. And so what are we doing for our output plot? Well, what we're going to do is we're going to say create a figure which contains 2 rows and 3 columns. We then want it to be 12 inches wide, and then we want to adjust the height in such a way that it reflects both the original image and the fact that there are 3 columns and 2 rows. So the easiest way to do this is to multiply this 12 by 2/3, and then multiply it by the aforementioned aspect ratio. This will ensure that the plot is correctly scaled. Next, we want to keep track of our individual images, so we'll go ahead and create an array that's the same size as our axes. So what we can do here, if you look at what our axes objects are, it's an array of 4 different axes objects. What we can do is go ahead, give it a numpy.empty-like, and pass it to the axes, which upon running this, we will see that our images are stored as an array of the same size as the axes. So the axes are the axes objects, and the images will be the actual images that are plotted. And as you see, we've already created our template. So it contains 2 rows and 3 columns. We need to go ahead and populate those arrays. So the easiest way to do that is as follows. So we're going to index it through the iter tools, so 2 rows, 3 columns. We're then going to populate our images with a blank image from the axis plot. And we'll be using imshow because that's how we show an image in matplotlib. We'll go ahead, give it the correct extents, give it a color map of grey, and we'll have to supply it with an empty image, but that's easy because we can do numpy.zeros_like. Then we can pass it the original image, which was im2, or the image that's cropped correctly. You can pass it that, and that will create an array that's the same size, filled with zeros, and the same data type. Go ahead and plot that. We see now we have successfully plotted all 6 of our plots with just a blank array. If we go back to the image at the beginning of the video, we'll see that we'll need a few titles. So DFT 8x8 on the left to describe this bottom row, full DFT to describe the top row, and then the original image, a placeholder for a variable that will show the amount of data we're using, and a reconstructed image on the right. So go ahead and just copy that over. See here we're saying axis 0, 2, I'm going to set the title to reconstructed image. Axis 1, 0, going to set the title to the description of the block size. Also give it the original image. And that's everything we need to describe our images. Good. Now there is one thing we need to do. We need to go back and we need to calculate the DFT. So we already did this in our from the code we copied over from our last video. And remember we called it the full FFT. What we need to do now is we need to make sure all the plots have these correct axes. We could go over and do this for each plot, so we know from our original image, from our video at the start, we know that the image goes from 0 to nx and 0 to ny. We know the DFT, we're going to plot this so it's shifted in the middle, going to go from minus n/2 plus 1 to n/2. The image on the bottom is going to go the same as the image. So this one here is the odd one out. Let's go ahead and set those limits. We need to get rid of our previous definition of extent, so we need to go back to saying plot from 0 to nx and ny to 0. When we plot that, what we'll see is that we've got the correct limits on our plots and also the correct extents, but we still need to sort this one out, so this single image here with the odd one out. So we can go ahead and just do one special case for that. To do that, we'll just do an if statement inside the for loop. And a pro tip to all new players, you don't have to do an if-else statement inside a for loop. If there's nothing that follows the else statement, you can just type continue, and that will continue the execution of the loop after this statement. So we'll go ahead and plot that. We see we've got exactly what we want. The original image is on the left, the correct extents. DFT is in the middle with the DFT at the top, that's going to be shifted. And then the reconstructed image on the right, currently set with nothing in there. We'll go ahead and copy over the code, which was responsible for the sorting. So if you remember, we want to sort it so that we pick out the smallest elements first. So we're going to sort both the full FFT, which we've defined here, and a block-based FFT, which we need to redefine. What we'll do is we'll take the code from the original image, but then we'll modify it slightly. So before, where we had a matrix that was number of blocks in the X, number of blocks in the Y, 8 by 8 for the size of the array, so 4-dimensional array that indexed each individual block in the image and then each individual DFT basis function. we're going to do it so we just have an image with the same number of pixels as the DFT, but each of those, that image is going to be broken up so it only calculates the DFT for every 8x8 block. Okay, so if I go ahead and run that, what we should have now in our variable explorer is the indices that are sorted in ascending order of magnitude for the block-based DFT and for the full DFT. Good. What we're going to do now is we'll just copy over again some code, which will just be a rehash of our previous animation functions, and we can tidy this up. So we're going to be sending it a tuple which will contain the frame number, which will be used for saving, and n, where n will count down, so basically telling us how much of the data to use. The image, we'll send it the full FFT and the block FFT. Remember these things we've just defined. And we'll do the same as we did before, where we take the FFT and we use this argument sort, and we pick out the n number of elements. When n comes in, it will be large, so it will go from big N to big N, set all the elements equal 0. So once n elements equal 0, then we'll go ahead and set those arrays in their correct position. So this one is images, top row, first column. Block-based DFT, the one below it. 1, 1. We then need to go ahead and actually perform the inverse fast Fourier transforms. So the first one is we're going to take a temporary array, because we need to do it on a block-based fashion, so it's not just simply doing the DFT. We need to tell it to iterate over the size of the blocks. So this is going to go for 0, 8, 16, etc, etc. It's then going to, in this temp array, which you've set as 0, for each 8x8 block in the temp array, it's going to look at the corresponding block in the block-based Fourier transform. So I'm going to do the inverse discrete Fourier transform, scale it with the right scaling factor, which is the block size squared, and then set that equal to that part of the block. And likewise, we then need to set our reconstructed image on the right to reflect this. We then need to tell it that we want to draw the canvas, and we'll also set this variable that we had from our previous video, where it's telling us how much of the original data remains, because we have access to this n, which is going to count down from big N to 0. We just need to copy over our animator. And you see now we need to redefine this frame. So before we had the argument sort, which basically was our frame, so we could just count through the arguments that are removing. But for this video, we're going to do something a bit different, because potentially these could be a lot of frames we need to iterate through. So this is very similar to our first video. We were doing full DFTs, because part of this is a full DFT. So what we need to do is we just need to find a way to represent frames a bit better. And there's a good technique here. So what we can do, what we want to do is let's set a number of frames that we want to output, n frames. We want to output 200 frames total. Then let's go ahead and just create something called frames that will have a property of length. So we'll just create an array of length 1. And then we're going to do something like this. So this length of this array frames will be 1, and then we're going to come in this while loop that will say while the length of all the unique values of frames is less than the number of frames we want, keep going. What we're going to do there, so what we want to do is we've already seen how the image is basically unrecognizable. So as you remove 90% of the data, the image is basically unrecognizably different from the original image. So we want to capture more of the data loss from the lower values. Ideally, we'd want some frames that would start counting down in big chunks, and then those chunks would get smaller and smaller and smaller as it approached 0. So one good way to do that is to do a Logspace. So a Logspace is an array that will logarithmically decrease the spacing. So for example, every 10 elements might decrease the number in the array by a factor of 10. So 0 to 10 might decrease by 10, 10 to 20 might decrease by a further 10, 20 to 30 might decrease by a further 10. So by the time you get to 30 elements, you're using 1,000th of your initial value. And the problem with that, so if I just go ahead and plot, so let's just go ahead and do it without doing this fancy while loop. So let's just write Logspace. Let's do frames equals pi.logspace. Remember we want to count down, so we're going to count down from n. But in the Logspace, we need to get the log of n. Let's do log of 10 of n. The count down to log 10 of 0. So some of the eagle-eyed viewers may already know this won't work. And let's create n frames. and we want integer values only because this frame should be an integer. If I go ahead and run this, not going to work. Or it might work, but it's going to complain because the log of 0 is undefined. So there's no logarithm of 0. So we get an instantly bad value here, and it proves the array. What we need to do is we need to add 1 to both of our values. So think of this as 0 plus 1, then do n plus 1, and then we can always take 1 off the answer. Go ahead to work that out. Now look at our log space. It goes from n, the big N here, which was 8192. It counts all the way down to 0, but you'll see we have a lot of zeros, a lot of 1s, a lot of 2s, and then it starts, as the spacing gets further and further apart, you start seeing this less and less. And this is useless because in our plot frame we want every frame to show something new, and so this isn't very useful. A really easy way to fix this, use numpy.unique. That will only show the unique values for a given array. And what you'll see is it gives you unique values, so 0, 1, 2, it's stripped out all the repeat values, but now it's no longer 200 elements long, it's 151. And we could go and keep doing this until we get to the point where we find a number of frames that give 200 elements in this frames matrix, in this frames array, but that's incredibly inefficient. So the easiest way to do this would be to do something like this while loop. So we're basically saying while the length of this frames, this unique value of frames, is less than the number of frames we actually want, what we're going to say is try and work this out. So give it this log space, work out an array with a given number of frames, and we'll call this ntemp, so temporary value of n. And we'll start that off by saying it's n frames. So we'll try starting at 200, but we'll see that we'll need progressively more and more. And then when it works out this log space, which we'll call frames, if that log space does not contain 200 values, it will keep iterating over this loop, and then we need a way to break out of this loop. And our break is basically going to be keep increasing ntemp by 1 until the number of frames is greater, or is at least equal to the number of frames we want. Let's have a look. You see now frames, and remember to set this equal to a unique. So do numpy.unique frames after that loop. We'll see now frames is 200 elements long and it contains only unique values. Problem is with unique, it will return them sorted from smallest to highest, but we want the opposite. Quite easily sort this by doing something like this. Good, so we now sorted our frames from largest to smallest in logarithmically spaced values, but uniquely. So we'll see more of the information when we've removed a lot of our array than we will at the very beginning. Go ahead and see what that looks like. Now see, we're not seeing anything, and that's because in our original plot we said plot these 0 arrays, so plot nothing. But obviously when we actually plot it, we're going to have an extent, so the colour itself will take a value between 0 and 1. So we can say vmin equals 0, vmax equals 1 when we define the images originally. Go ahead and plot that. Still not working. And there's a very good reason for that. It's because even though we've said it varies between 0 and 1, we actually go ahead and plot the logarithm of that value. So that's not going to vary between 0 and 1. So a really easy fix for that is just let's go and reset the image limits every time we come into the plot. To do that, we get the handle to the axis and then we tell it to update the color limits. So it's the middle two plots that will cause us issues. We'll go ahead and just get the minimum from the array that we've just placed inside of it. Go ahead and do that for both of them. And it's actually the image object we need to change, not the axis object. We need to make sure we get the array that we've just set for those images above. Go ahead and plot that, and this now should work. Good, so we've got the DFT in the middle, in which we're scaling the colour every time it goes over a frame to reflect the new minimum and maximum values. Likewise for the block-based DFT at the bottom. and we're successfully reconstructing the original image on the right, and the original image on the right has the extents of the original image, so that will reflect any brightness changes that are associated with adding the elements from the DFT. The last step is to put our original image in, and we know that our original image doesn't change, so we can go back to the top where we plotted our blank arrays. We can give it another condition, which is basically if j equals 0, so the first column. And for this one, we just give it the original image. We copy that over, and rather than make a 0 copy of image 2, we give it image 2 itself. No longer need to manually set the extents, but we will take it as a normal image. We'll continue so we don't execute the rest of the loop. And you'll see we've not needed to do an elif statement, because in each if statement we've basically said continue out. So it's the equivalent of, say, maybe in C doing a switch statement in which you was only comparing one value and then having break under each statement. Go ahead and plot that and get exactly what we want. So on the left hand side we have our original image. On the middle top we have our discrete Fourier transform, which is then being decimated. So we're removing the components with the lowest magnitude, starting from the lowest magnitude components and working up to the highest magnitude components. We're doing the same for the block-based DFT, and then for each of these DFTs we're reconstructing this image based on the fast Fourier transform of this DFT here and this block-based DFT at the bottom. And this is really nice because now we can see exactly what happens as we remove the same amount of data between the two different transform methods, the block-based and the non-block-based. And you can see how it behaves differently. So for a text-based image, inverse Fourier transforming the full DFT leads to artifacts, but they tend to be quite smooth, but distributed across the entire image. You can still pretty much make out the text, but we're getting all these different artifacts. And as we logarithmically decrease the amount of data that we use to represent the DFT, you can see the reconstructed image becomes worse and worse, to the point where we have a lot of trouble reconstructing the original image. So now it's become illegible, all the text looks the same, which isn't very nice. Whereas on the block-based approach, so let's go ahead and play that again. Let's look at the bottom plot. So on the block-based approach, as we start to reduce the data, and you notice both plots look pretty good until we get to around 10%. But with artifacts appearing on the reconstructed image from now, basically, we can see them. As on the block-based DFT, they start appearing now, in which we're only using 25% of the original data to reconstruct the image. As you see the block-based DFT, you can start seeing the actual outline of the 8x8 blocks that were used to reconstruct the original image. And it's still legible, so we'll just go ahead and watch this play. We'll see when which one becomes illegible first. I would say about there it becomes very difficult, so that's about 1/40th of the original data that has been used, so that was around 2.5%. It started to become very illegible to actually reconstruct, to read the text on the reconstructed image. Let's go ahead now and do some interesting things. Let's change the block size to something bigger. Now you can see I have much bigger blocks, and so the decimation of data should start earlier for the block-based DFT at around 50%. So we should start leaving data now. But you can see the reconstructed image still looks good, whereas for the full DFT reconstruction, we started having artifacts much earlier. So again, it appears that this block-based DFT is doing a very good job for these text images. And we can see we get slightly different behavior, but now the blocks are larger and more visible. Go ahead and change the block size to something small, like 2. So this is now a lot different. You can see you can almost make out the original text in the discrete Fourier transform domain, which makes sense because we basically broke the image into small blocks and then Fourier transform them. So where there's going to be data in the original image, there'll be data in the discrete Fourier transform. But we can see that as we're removing data, we can still make out this original image perfectly. So none of the block-based DFT has been decimated yet, and we're at 13% of the original data. So it would appear that a smaller block size is actually better for these text-based images, which kind of makes sense. But then as we start to decimate data in these block-based images, we can start to see how the image degrades in a block-based fashion. And so you could argue that smaller blocks, why not use smaller blocks? Surely they're better. Well, at the end we'll discuss something about block size. But you can see how it changes. And it's really nice, you can still make out the text, the ABCD, in the block-based DFT. Okay, put block size back to 8, go back to our ducts, and we'll see what happens now. So we already showed how block-based DFT was actually very good for digital photographs. There was barely any noticeable change in the image after adding just a few components to each block. Now with this animation, what we're doing is we're basically choosing the smallest components across all the blocks and removing them first. So what we should see is that we get an even better representation in the reconstructed image, because we really are removing the components that matter less and less. And because digital photographs are quite complex images, it'll be much harder to see individual changes in small blocks. We can see now we're using about 1/20th of the data from both the full DFT and the block-based DFT. And here's where we start seeing artifacts become evident. So in the reconstructed image from the DFT, we can see that we're getting quite a lot of grain, especially around this middle duct. The image overall is becoming quite grainy, as we're now up to about 1/50th of the data from the DFT. And for the block-based DFT, we're getting blocking artifacts around some of the ducts. So particularly where there's edges, we start to lose some detail, and it becomes blocky. But we can see that the block-based DFT is just as good as the original DFT for reconstructing images, but has the advantage of being able to reconstruct text a lot better. So you can see now why in things like JPEG compression, the block-based discrete cosine transformation is used, because it has several advantages for all types of images. So it still preserves digital photographs very well, but also has the advantage of being able to reconstruct text very well. So what did we learn from this? Well, let's go over what we did across the entire series. So in part 1, we learned how the DFT takes an image of width by height, produces another image of complex components, and for each one of those pixels on the discrete Fourier transform, you can generate a full image, which is called a basis function, which describes the spatial variation in both the x and y direction, and adding those up with the amplitudes from the DFT can construct the original image. In part 2, we saw different ways in which we could potentially remove information from our image. So a type of, I don't want to say compression, but a type of decimating the original image, or removing the amount of data needed. We saw that removing pixels and changing bit depth was very good for text-based images, but wasn't very good for digital photographs. And then in part 3, so in the last video, we saw how we could, instead of doing a DFT for the entire image, we could break the image down into smaller blocks, for example, the 8x8 blocks. And that had the advantage of producing significantly less global artifacts on text-based images, making not a lot of difference to a digital photograph. And we also saw that you require very little of the actual DFT components themselves per block in order to reconstruct the original image. And in this video, we've basically gone ahead and done a comparison between if we take in an image, perform the DFT, so the full DFT, and the block-based DFT, and then start removing components by absolute magnitude, starting from the smallest to largest. We see how we can reduce the amount of data needed to reconstruct an original image. And what you typically find with things like this is that you only need around 10% of the data in the DFT in order to reconstruct the original image. And remembering that the DFT is the same image size as the original image, but just complex. So it takes basically the same amount of information to actually represent an image in the discrete Fourier transform domain, so in the Fourier domain. And so by removing information within the Fourier domain, we're essentially reducing the amount of data required in the image. And what's actually more important is if we look at how reducing the data occurs, you can see that for the DFT, we reduce a lot of the values around the edges, spiraling inwards. And likewise for each one of these blocks, what we would find is that you start from one corner, or the highest frequency components first, and move out to the low frequency components. And so from a compression point of view, these are actually two very good methods in order to compress an image, because now you've got the situation where you need around 10% of the data to represent the original image in your reconstruction from the discrete Fourier transform, whether it be block-based or full. But the actual place in which you've removed that data is predictable and itself comes in large blocks or large chunks. And by being predictable, that really helps with compression algorithms. So compression algorithms like things that are predictable and things that are bunched together. So now you can sort of see why, for example, JPEGs use the discrete cosine transformation, because doing things in the Fourier domain and then choosing how you compress things and what parts to remove you end up with highly compressible data structures. So I hope you found this multi-part video series interesting. Congratulations if you made it to the end. It's been quite long. I suspect it's well over an hour and a half by now. But I want to say thank you for watching, and I hope you found this interesting. I will put a few of these videos on the channel, and I'll put the code in the description somewhere. I'll start a GitHub repository somewhere if I haven't already started one, so anyone can download this and try these for yourself. So yeah, thank you for watching.